we're going to talk about lesson 1 of our thermochemistry unit. So as you'll see here, the first thing that's important here is the definition of heat. So in case you've never heard this officially before, heat is defined as the energy that transfers from one object to another because of a temperature difference between the objects. So we'll be talking a lot this unit about the system, which is the part that you're interested in, versus the surroundings, which is everything that's immediately around the system that we're interested in. That'll make more sense as we start doing problems in labs with this unit. So the first thing here we need to make sure we have is a definition for endothermic and exothermic. I'm assuming you've heard of these before in bio, but just so we have official definitions. Endothermic means that heat is absorbed from the surroundings. So for example, if you're near a fire and your body, which is the system we're looking at, absorbs heat from the surroundings, which would be the fire. And in this case, Q would be positive. I'll talk about Q more in a minute here, but Q is going to be a measure, a variable that stands for heat. So exothermic would be the opposite. So heat is going to be released to the surroundings from the system. Okay, so it's released to the surroundings. So an example here would be if you look at the body again as a system, when you sweat, you release heat from your body to the surroundings, which would be air in that case. And Q then would be negative. So next we're going to talk about calculating heat and specific heat now that we have those definitions down. So specific heat is going to be the amount of heat it takes to raise the temperature of 1 gram of a certain substance 1 degree Celsius. Now this will be different for each substance. So as we talk about specific heat, it very much depends on the substance we have in play here. So we have an equation for this. So for our equation here, we're going to deal with the following variables. So Q, M, C, and delta T. So our equation is going to be, this pen set up here. So it's going to be Q equals M, C, delta. Okay, so all of the variables are in this table here, so we're going to take a minute to define them. So if we look, Q is going to stand for our heat, and it's going to be measured in joules. All of the units are going to be important, just as they are in any other unit. M is mass, that should be measured in grams. C is going to be the specific heat variable that we have to play here. The units for this are joules per gram degree Celsius. Okay, so I'll enter this degree sign here. And then delta T is going to be change in temperature. When you do problems, you're going to take the final temperature minus the initial temperature for this calculation. Think about that delta as the change like you've seen in math when you think about slope or anything like that. So since it is a temperature, we're going to use a unit of temperature. Unit we use degrees Celsius. Okay. All right, so we're going to start practicing this. So examples, how much energy does it take to raise the temperature of 15 grams of water, 25 degrees Celsius? Okay, so we're going to use the only equation we have, which is Q equals MC delta T. Okay, so we've got Q MC delta T. Looking through the problem, we need the energy, which is Q. Does it take to raise the temperature of 15 grams of water? 15 grams of water would be our mass. This is our change in temperature. So the one thing we're missing here is our C value. Either the problems for this unit are going to give you the C value or I will give them to you. So one thing you should know is for water, this is only for water, the C value is 4.18 joules per gram degree Celsius. 4.18. Okay. So plugging things in now, we need to solve for Q. So our mass we plug in is 15 grams. Our C is 4.18 joules per gram degree Celsius. Our delta T is 25 degrees Celsius. Go ahead and calculate that out. You should get about 1,567.5 is heat. So your units here should just be joules. All right, let's look at a different problem here. The initial temperature of 75 grams of water is 25 degrees Celsius. What would the final temperature be if you have 500 joules of energy added? Okay, so notice we're using water again, so it'll be the same C value that we had up here. This is our mass, of course, because it's in grams. We have the initial temperature here, so we'll use that to find delta T. We need the final temperature, and then this is our Q. So the first thing we need to do is find delta T. So Q equals MC delta T. So you can solve for delta T first if you're comfortable doing that kind of thing. Okay, so you divide both sides by MC to get delta T by itself. So delta T is Q over MC. Q would be 500 joules from the problem. Our mass is 75 grams. and our C is 4.18 gram degrees Celsius, just like it was in the last problem. That means our delta T is going to be 1.5595 degrees Celsius. Okay. So what we need to do then is we need to figure out, okay, if that's our delta T, that's not what the question's asking for though. Our delta T is 1.595, but we need our final temperature if you look back at that problem there. Okay. So to get our final temperature, so our delta T, like I mentioned, is the final minus the initial, okay, as we wrote in the table, or you should have written the table up there. I can see where that would be. That comes from right here. So final minus initial. Okay. So using that idea, our change in temperature is our final minus our initial. We know our initial temperature right here is 25, and we know our change in temperature. So I'll plug these things in. So our change is 1.595. We don't know our final. We know our initial is 25. So to figure this out, we need to add 25 to both sides. So that means our final temperature is 26.595 degrees. And that would be your answer. All right, so switching gears a little bit. When we talk about heat, we're very interested in different phases. As you change different phases, there needs to either be heat added or heat released. These are all exothermic and endothermic processes, to say it a different way. One thing that you may not have known, there is a word for the phase change that goes directly from solids to gas. You may not have heard a lot about this, but it's called sublimation. And likewise, the reverse would be deposition. Okay. And then triple points and critical points are going to be important as well. So looking at this phase change diagram here, you've got the three phases here. So that's clearly solid. Hopefully that's pretty self-explanatory. Liquid and then gases. You can label what it's called to go from solid to liquid with this arrow right here. If you go from solid to liquid, you're melting. Liquid to solid, then this arrow would be freezing. Liquid to gas, as you have liquid that evaporates into a gas, that's called evaporation. Reverse, gas to liquid is condensation. That should be a pretty much a review. What it's showing you here is you add energy by going this way. Okay, you would release energy going this way. So like as you go from a liquid to solid and you freeze, you lose energy. It's an exothermic process. This is just another way to look at these phase changes. Okay, but what's really important is that you know how to do these kinds of phase change diagrams. Okay, so these give you a lot more information because they deal with both pressure and temperature. We talked about pressure a lot in the last unit as well. So looking at these guys here, on the left, this is just an example of a specific phase change diagram for water where you have ice, water, and steam. On the right, this is a generic one where you've got solid, liquid, and gas. What's important here is that you know that in this area that's all green is a solid phase. Underneath these lines where it's all orange is all gas, in between liquid. What's important is the triple point, which is right here where the three come together. Again, labeled as a triple point here. This is where solids, liquids, and gases exist in equilibrium. You can read those temperatures and pressures if you read down the line, okay, where that exists. And then this critical point up here, where these two end, you'll see that this line does not continue out. That's because once you get past these certain conditions where you've got 72.9 atmospheres of pressure and 31 degrees Celsius, it's actually impossible to tell whether you have a liquid or a gas at that point, and that's called a supercritical fluid. Okay. Now you can add the other phase changes in here. So if you draw a line going from solid to gas, we just learned that as you go from solid to gas directly, that's called sublimation. The backwards way, gas to solid, is deposition. You can draw in your solid to liquid phase change, which is called melting. Backwards would be freezing. And then you can do liquid to gas and gas to liquid as well. Okay, so you could label this in here. So we're going to be talking a lot about these phase changes using these kinds of diagrams in this unit.